Hello, in this video we're going to begin our discussion of oxidation reduction reactions in the second semester Gen Chem version. So first I'll remind you just what these types of reactions are, and then we'll talk about oxidation states. Okay, so an oxidation reduction reaction, we call this a redox reaction because that's a lot easier to say. And this is a reaction where electrons are transferred during the chemical reaction. So here's our simple example. You have sodium and sulfur, and you put them together to make sodium sulfide. And well, sodium has 1 valence electron, sulfur has 6 valence electrons, so if each sodium gives its valence electron to the sulfur, then that leaves all the sodiums with a positive charge, and then now your sulfur has 2 extra electrons to give it a -2 charge, and then both of these atoms in the ionic compound have full octets, which is preferable. And so we could look at the charges on each one of these and say, all right, they start out both at 0 because they're both elements. And then in this ionic compound, you have a +1 charge on each sodium and a -2 charge on the sulfur. And so this is old news. You've done this before in the first semester of Gen Chem, but I'm just reminding you of how this goes. And so we have terminology that goes with this. Sodium loses electron and thus it's oxidized. The origin of this term had to do with bonds to oxygen, but then as chemists started to know more about chemistry, then it became a broader term than that. And then the opposite of that is reduced. So sulfur, in this example, gains electrons and it's reduced. You have some mnemonics that can help you with this. One common one is oil rig, and that says that oxidation is loss of electrons, and then reduction is gain of electrons. So sulfur is reduced because it gained electrons. It went from 0 to -2, and that's adding electrons because electrons are negative. The way that I remember it is I go with this first. So whichever one has the charge that's reduced, that's reduced. So 0 to -2, that number goes down on a kind of absolute sense. And then if you go from +1 to 0, that number goes down, right? So I remember these things by looking at the reduced one first, and then whatever the other one is oxidized. So the number goes up when it's oxidized. However you want to do it, as long as you remember it, it's okay. So one other little thing is that we call sodium the reducing agent because it's the agent that makes the reduction happen, even though sodium itself is oxidized. And sulfur is the oxidizing agent. It makes the oxidation happen by itself being reduced. And so effectively, if you look at the same element here, sulfur is reduced and it's the oxidizing agent, so it's the opposite one. Okay, so again, that's old news from the first semester of Gen Chem. And now we're going to expand on that by talking about oxidation state. This is also called oxidation number, depends on who you ask. And so basically the oxidation state is charge, what the charge would be on each atom if the electrons were transferred completely from one atom to the next. And so for ionic compounds, it's really straightforward. Whatever the charge is, because we know this explicitly for ionic compounds, then that is the oxidation state, right? So if you look at sodium and chlorine, the oxidation states are 0 before the reaction, and then sodium's +1, chloride's -1 after the reaction, which is just the same as their charge. And this makes perfect sense for an ionic compound because the electrons are actually transferred completely. Now, if you make a molecule, then things are a little different. We know that this is a covalent bond between this molecule, and the electrons are shared. They're not actually transferred. But for bookkeeping's sake, we want to have some number that we can use to describe oxidation reaction reactions. And so we need to have some number. And so we just imagine, what if the electrons were completely transferred to the more electronegative element? And so for this reaction, sulfur starts at 0. Here we would assume sulfur's +4. Oxygen starts at 0. Oxygen goes to -2. And we basically just treat it like it's an ionic compound, even though it's not. So it's a little weird, but it makes sense. It helps for a bookkeeping thing for oxidation reduction reactions. Now, we've also talked about formal charge. This is the last time we put pluses and minuses around formulas, and it's a very different thing. It overall is calculated somewhat similarly, not the same, but it's conceptually for different things, and I'll talk about that a little more. And then this is my little warning box that says this is easy to do for ionic compounds, but it's a little weird for molecular compounds, which I just said. So how do you do it? For the ionic case, it's very easy. You already know how to do that. For the molecular case, it's a little harder, so we have to put some rules in place. And these rules also apply to ionic compounds as well, so it's kind of a universal rule set. So anything that's a free element by itself has an oxidation state of 0. That makes sense. It'll have the same number of protons as electrons, and they're not shared unequally in any case because both of these chlorines have the same electronegativity, so it's not going to unequally share them based on electronegativity. All right. Now, when you add up oxidation states, it equals the charge on the compound. This sounds familiar from things we've done before. And so if you have sodium chloride, right, the sodium's +1, the chloride's -1, that adds to 0. If you have the nitrate anion, well, in this one, it turns out the oxidation state for nitrogen's +5, oxygen's -2. You add these together. Since you have 3 oxygens, you have to multiply by 3. And this gives you the overall charge on the ion. So this is very similar to formal charge in this kind of idea. But now it gets different from formal charge as we go a little further. So we're not just sharing electrons equally when we talk about formal charge. Instead, we're doing it based on electronegativity. So we summarize this as, here's a priority order. Right, certain things want to get their certain oxidation state, and some of them win, some of them don't. Oftentimes it doesn't really matter. For example, you might have oxygen, and then, well, you have something else that's not on this list, and then you just use the charge of oxygen and the total charge on the molecule to figure it out. So oftentimes you don't have to worry about the order here. But the order should make sense, right? The alkali metals are +1, fluorine's -1. This matches our kind of sense of ionic compounds. Alkaline earth metals are +2. Hydrogen's +1, oxygen's -2. So the charge here makes sense. And so here's some examples over on the right too. So the preferred oxidation state is just the charge that it would want to take based on the periodic table. You got -1, you got -2, -3, right? +1, +2, etc. And then the priority order of who gets the charge they want is determined roughly by electronegativity. It's not quite right. But the alkali metals, most of these are very close to 0, so they're very happy to lose that electron. Fluorine is 4, it's the most electronegative element, so it's going to take that electron. Oxygen's fairly electronegative. Hydrogen's kind of out of order in terms of this, right? Hydrogen's kind of in the middle between 0 and 4, but it gets its priority before oxygen does. So that's the one thing you really have to remember. Everything else should just kind of fall in place as it would make sense. Then any element that's not previously described here, you can usually figure it out by, okay, you have one thing you have the total charge and you can do some math. And that's the level to which I'm going to personally take it in this course. The next step beyond this, if you have, say, 2 things that are not on the previous list, and you have to figure out what each of these elements are, you draw the Lewis structure. And then you assign all the electrons in the bond to the more electronegative atom, right? So this is different than formal charge. And then you can assign the oxidation state with this formula. Now, this is something that you don't need most of the time. It's only pretty rare that you actually need to do this. And I think the complexity is not worth complicating the idea of oxidation states. So I'm personally going to skip it. Likely your chemistry professor, if it's not myself, is not going to skip this. And your textbook has a good description of how this works. And it's a good refresher on Lewis structures. Okay, so let's try this. Let's do some practice. So give the oxidation state, or number, same thing, for all atoms in the following. All right, so we look at sodium oxide. This is an ionic compound. Sodium is an alkali metal, so those are always +1. Oxygen prefers to be -2, and nothing's stopping it from being -2 in this case, because if you add this up, you have 2 sodiums, and you have 1 oxygen, and that adds to 0. The overall charge on this thing is 0, so perfect, that works. All right, next, the chlorine trifluoride. So on our list here, we saw that fluorine's -1, so we start there. And then we use the other rule that says when you add these all together, it has to be equal to the charge. And there's no charge on this molecule overall, so this is equal to 0. There's 3 fluorines, so you have the 3 right here. And now we just need to solve for x, or question mark, right? So this is going to be +3, because then that makes this equal to 0. All right, the phosphate anion. Well, the place you can start here is with oxygen. Since the phosphorus was not on our priority order list, we know that, all right, oxygen's going to be -2. It's more electronegative anyways. And then, well, the math here would say you have 4 oxygen atoms. Each one's -2. The overall charge on this is -3. And so whatever this number is, in order to make this math work, is the oxidation state for the phosphorus. And it turns out that's 5. 5 minus 8 equals -3. Now this one, the arsenic acid, it's called, well, let's see here. Hydrogen was first on our priority list, so it's going to get the +1. Oxygen was next on the priority list, so it's going to get -2. And then we can use this plus the rule that says they all have to add to the charge, which in this case is 0. There's no charge right here. And we can use this and basically solve for x. And when you do that, it turns out that your x is +3. Okay. Now for the last one, we're going to start with the oxygen because we know what that is. But now we have the problem where, well, we can't determine the sulfur and the chlorine at the same time. So this would be an example where you need to use Lewis structures. And we're not going to go there, so I'll just skip this. And I'll tell you the answer. It comes out to be like this. But that's the next step, right? If you can't do it with just these rules, you would go to the Lewis structure. All right, so that's basically the concept. So now a couple different thoughts at the end here. This is different than formal charge, right? The calculation of how you do it is fairly similar except for this. In formal charge, you're splitting the shared electrons between both atoms. And for the oxidation state, you're assigning them to whichever atom has a higher electronegativity. And so in this chapter, we only care about oxidation state. I just like to make it clear with a fairly similar looking thing that you've done before. And so formal charge is the bookkeeping tool for Lewis structures. Oxidation states are the bookkeeping tool for redox reactions, just seeing where electrons are, where they go, etc. Oxidation states do not have to be integers. It seems a little weird, but it works. And metallic elements are generally always positive or neutral. And nonmetals can be anything. They can be positive, they can be 0, they can be negative, etc. Now, also skip the part about using Lewis structures to assign oxidation states in your book, because again, I said we're not going to do that. And that's all I have for this video. Thanks for watching.